some items are often overlooked in the delegated design process. So the manufactured glazing systems are primarily storefront curtain wall, and there's two types of curtain wall. There's unitized and there's also stick built. So primarily the storefront is a screw spline type of a system. It's screwed together very tightly. It's used to span between floor systems and spans up to 8 to 12 foot, so floor to floor. And it depends a lot on whether horizontals are used in the system design, whether or not it can span 12 foot or not. And it requires expansion joints every 20 to 25 foot in general, horizontally. Curtain wall, as I indicated, consists of two different types. One is a stick-built type. This is usually built on the job site and comes in lengths of sticks. Typical depths for this type of curtain wall is 6 inches, 7.5, and 10 inches. And this typically will span up to 20 to 24 foot. And the 24 foot and the 20 foot spans, that usually requires a very heavy and deep mullion, and usually it's reinforced inside of it. And so typically this is very limited to structural building movement. The unitized curtain wall typically comes in the same depths as the stick built, spans 15 to 18 foot depending on reinforcing. This is usually used for high-rise construction. It accommodates greater structural movement, primarily due to the deep joint. Usually at the floor lines, it's associated with the unitized system. And usually this is shop fabricated to high tolerances. And so it usually is limited in characteristics of the architectural aesthetics in a kind of a regulated way. In other words, stick built, you can get more geometries and more different shapes on the outside of the building than you can with the unitized type curtain wall. So that's primarily the different types of manufactured glazing systems. And we're going to cover one of the major limitations associated with these manufactured glazing systems in a moment. But let me define delegated design. It's usually the shifting by contract law of various design responsibilities from the architect or engineer of record to the general contractor. And so my question about this is, with reference to building structural movement, does this always get done? So inside of your specifications, you should have some information that looks like this about the delegated design of glazing systems. And this can be in all kinds of different glazing system sections. Even the insulated glass can have a delegated design criteria requiring it to go out to another engineer, a third-party engineer, to be able to perform the calculations associated with it. In reference to storefront and curtain wall, it might look a lot like this. And so we're required to look at structural loads in the design, thermal movements, but here's the big one: movements of supporting structures indicated in the drawings, including but not limited to story drift and deflection from uniformly distributed and concentrated live loads. This is the one where it gets overlooked quite often in the delegated design that I want to bring your attention to. So your specification may contain a small part that looks like this in the action submittals that requires a delegated design set of calculations to comply with the performance requirements and design criteria to be submitted. The delegated design process usually looks something like this flow chart, where it comes down from the architect and owner in terms of the drawings and the specifications to the general contractor. From the general contractor, it goes out to a glazing contractor, and the glazing contractor has several different routes to get the delegated design performed for this glazing system. They have the opportunity to approach the manufacturer of the storefront or curtain wall, and they'll give them a product quote, and an option for shop drawings. And sometimes they'll include in an option for delegated design after the first submittal set of shop drawings goes back up the chain for approval by the architect. So ultimately, whenever the first submittal set of shop drawings gets done, it goes through that process, usually without a structural engineer that is in the glazing industry looking at it. It's usually a drafter or a detailer, and so it'll go back up the chain to the manufacturer, through the glazing contractor, back up to the general contractor, and to the architect for conformance review. And so ultimately, it has not seen a structural engineer at that point. And if the architect, owner, or the general contractor does not request a delegated design submittal for calculations, often that may get overlooked in the process. So the glazing contractor also has some other options for getting the delegated design process fulfilled, and that's one through a shop drawing provider, and usually they can contract out to a structural engineer to look at it, or they can contract directly with a provider like JEI, and so they look at the first submittal set of shop drawings or post submittal set of shop drawings for that delegated design process. But ultimately, my point is here, if the architect or the GC does not ask for those calculations in the first set of submittals, oftentimes it could get overlooked. And in a lot of cases that I've known in the past, it has been overlooked. So I wanted to talk about some of the limitations associated with building structural movement and glazing systems that are manufactured. The story drift, or the lateral movement of the building for wind and seismic, is not so much of an issue. Usually this has been tested out with AMA 501 testing by the system manufacturer, and so it's not a big deal to get that to work. And there are ASCE 7 calculations for an engineer to be able to perform associated with that drift movement. The real important structural movement limitation that I want to bring to your attention is for vertical deflection at the bottom of beams. We're all very familiar with, the beam movement associated with cold formed steel walls or internal non-load bearing walls inside of the building. And in fact, we might see some type of a joint that looks like this that accommodates that beam moving downward associated with live load movements. But it's less common for that understanding to apply to the exterior of the building. But we have the same situation that generally applies to facade systems. And so in this view, we can kind of see, if you will, an X-ray through some curtain wall, and the X-ray reveals that in the blue, we would have the beams and the columns, and we can also see a deflected shape of a beam that is supporting the curtain wall. And so over to the side, we see a section of that and what that looks like, and we have spandrel beams that are associated with the section over at the side. And so often a manufacturer may designate that there would be different supports for the curtain wall and splices. And so this is a very common scheme that we see over here, where we have a wind load connection at the top and dead load connections at each floor with a splice beneath the dead load connection. And what that means is that for a dead load connection, we have just a simple bolt and a bracket that holds that to the structure. And so whenever this structure and the beam moves down, the curtain wall section that it's associated with has to move down, and it usually moves down into an expansion joint for the vertical mullions. And contrary to that, a wind load anchor connection will have a slot that's associated with it vertically, allowing for the building to structurally move. That beam moves up and down, and it does not affect the curtain wall on the outside. And so that's what I mean whenever we're talking about these wind load connections up at the top and dead load connections at each floor. The problem is being able to accommodate whatever this beam movement is. If we have a dead load anchor connection that basically this whole section of curtain wall is setting on that beam and it needs to move downward a certain amount of distance, that's the issue. Accommodating that beam movement in a downward direction due to live load, or if it's a roof beam, then it could be a snow load or wind uplift. So structural engineers of record are allowed to design the beams associated with a building for different types of deflections according to the code. L/360 is a common one used for floor beams and an L/240 for roof beams. What that means for a floor beam would be for a live load movement, they could actually design that beam that we saw before for L/360, and that would mean that a 30-foot beam would have about 1 inch of movement that we have to accommodate in the glazing system. So this beam would want to move down 1 inch associated with live load movement if it's designed with that criteria by code allowance. So the big question is, how much can a manufactured curtain wall stick-built system accommodate in terms of live load movement? In this case, we have a beam that it's attached onto with a dead load anchor, and this beam wants to flex downward 1 inch according to the code allowed deflection. So the only place that it can actually allow for that deflection is, number one, for the aluminum mullions that you see here that are actually connected to it. It's in a splice joint, but there is no splice joint associated with the glass that sits out in front. So the only place for the glass to be able to accommodate that movement is up in the glazing pocket. So how much do you think that that glass in the glazing pocket can accommodate for a manufactured typical stick-built system? That's the question. The answer to the question is, typically manufactured stick-built systems can only accommodate 1/4 inch maximum movement in that glazing pocket. And so this becomes a very big issue at the tail end of the delegated design process, where we have to go back through the process and ask the structural engineer of record who designed for the beam movement, what is the actual movement of the structure? What did you actually design for? Because if it's by code, that can allow way too much movement for these manufactured systems to be able to accommodate the 1/4 inch. There are some accommodations for this in the unitized curtain wall, as I said before. These can actually handle a lot more movement associated with building vertical movement, anywhere in between 3/4 of an inch up to 1.5 inches. And that usually is very limited, though, in nature, because this joint size and this profile becomes extreme. And that follows around the building, usually at one spot, usually at the floor line. And so there's a lot of difficulties associated with geometries that are wanted by stick-built systems in terms of unitized systems. Whenever we switch over to unitized systems, it's not a flexible arrangement with unitized. Just to kind of prove the point, here's a manufacturer's quote, and you can kind of see inside of the quote that they have a limitation to accommodate a maximum of 1/4 inch. And so that's one manufacturer. Here's a manufacturer's shop drawings, which actually has a embedded area in it that identifies design criteria. Down at the end of their notes in a very small type, it basically says that the standard curtain wall systems can only allow a maximum of 1/4 inch building structural live load movement. Here's a different set of manufacturer's shop drawings just to prove the point. Most all of these have this in there, but this one also has the limitation of the live load deflection at a maximum of 1/4 inch. And also they add in a note that if you approve it, that you have effectively approved changes to the scope of the design. So a lot of times the manufacturers will go out and they'll hire structural engineers, companies like ourselves, to do the delegated design process. And this is an actual excerpt from a different structural engineer that has performed the design, and they indicate right here in a note in their design criteria that they have assumed a 1/4 inch maximum combined building structural live load and deflection. So my question to you is delegated design really being done associated with the performance requirements by contract that are issued out? Typically, whenever manufacturers do this and they hire an engineer, they ask them to assume that it's 1/4 inch because that's all their curtain wall system is designed to be able to accommodate in terms of a stick-built system. And so they have that as a qualifying criteria. And the reason for this is that they have a sales cycle that really does not include the asking of the question about building structural movement. They make the assumption instead. There are some solutions associated with this that we have found in the past. And so one of the solutions would be to actually allow the systems to be stacked at the joints with a butt splice in the curtain wall from level to level. So the most that you can probably do this is probably about 3 floor levels, and then the thermal expansion at the top of those levels would need to be accommodated along with any movement in the building floor or roof live load. In this case, it would be the roof beam that is up at this level that would have to accommodate not only the live load and snow load of the roof movement, but also it would need to accommodate any thermal expansion for about 3 floors. That can create quite a large joint up at that floor line or roof line. A second solution to the structural movement issue would be for a horizontal, and some of the manufacturers have actually come out with this and developed this in the past few years as this has become a bigger and bigger issue with structural building vertical movement. They've developed this for stick-built systems where it includes a silicone sheet type of a joint. And so ultimately this can still lead to very large sight lines. So this would be very similar to a unitized system, but instead it's a joint for a stick-built type system. So these structural building movements also need to be accommodated at the head of the curtain wall system. Like I indicated before, there's thermal movement upward that needs to be accommodated in the expansion of the curtain wall. And if this is supported off of a beam, as in cold form steel, and we have a section of curtain wall that is over, say, 20 foot wide, usually this cold form steel up here cannot span over that opening by itself, and it has to be supported off of the structure and the beam, which does move downward with live load movement, or if it's a roof structure, it will have some wind uplift and some snow movement associated with that as well. So joints need to be designed to accommodate that same building movement and include the thermal expansion of the system. However, joint sealant from manufacturers typically can only crush about 50% of their design dimension and remain intact. In other words, if you try to crush this more than 50%, you're going to damage the sealant and it's going to rupture. And so that means for a 1-inch type of movement, that is the beam movement here, you actually have to accommodate that to only crush it 50% of its dimension, which leads to a probable 2-inch joint of sealant. So here you see that there is a formula associated with a joint sealant. This is the formula out of Dow design manual for their sealant. And this MT over here stands for movement due to thermal expansion. The MI stands for, or the ML stands for movement due to live load. You add both of those together, and then the X factor is associated with how much they can move or how much they can be crushed. And if it's 50%, you can see that there's a 2 out here. 100 divided by 50 equals 2. If we have 1 inch inside of this, it's 2 times 1. And that doesn't even consider tolerances that need to be associated with that joint. So you can see that this joint in a sealant joint becomes quite large very rapidly. Some of the things that we've seen in the stick-built manufactured area to accommodate this and to account for it are joint details that are similar to this, where it actually will have a silicone sheet that is up inside of the joint, and it allows for that building structural movement at the head. But this is very special. These have only been developed within the last few years by some manufacturers. So what about storefront and building structural movement? Oftentimes, storefront gets overlooked as well in the delegated design for building structural movement because it's the same deal. If we have cold formed steel and we have a storefront section that is wider than, say, 20 foot, this cold formed steel usually does not span over that independently and must be supported off of the beam above it. And that means that it must move with that beam and allow that building structural movement into that joint. So in this case, we see a standard architectural detail that shows a shim joint. Now, how much can a shim move? 0. It does not allow for any building structural movement. And so whenever this is shown in architectural details, it's actually usually in error because this usually requires building structural movement to be accommodated. Manufacturers have developed these receptors to allow for that building structural movement, and most of these receptors can allow anywhere in between 3/8 of an inch to 1/2 an inch associated with building structural movement. But you can see that that still does not take care of 1 inch. And so there's a lot of work that needs to be done in advance to make sure that we don't have this at the tail end of a delegated project where we have 1 inch of movement and a storefront system with manufactured pieces that will only allow for 1/2 an inch. And we suffer that sometimes in the projects that we are associated with. Many times you might have to move to a curtain wall system that takes the movement in a different way in a type of a T-anchor that allows sliding up and down inside of the pocket. We recommend for the building structural movement these considerations. Limit spandrel beam deflections, that's your outer beams that support facades, to 1/4 of an inch, and or provide a keyed table associated with the steel drawings that show the vertical live load beam movement, opening by opening. We recommend that the early design coordination with a glazing system consultant, that can be the manufacturer. Manufacturers have a lot of good information. And so the only thing is, they won't mention the building structural movement. You have to bring this up to them to ask about it and how that can be taken, because it doesn't fit their sales process that has been developed 20 years back. And so a lot of the delegated design has evolved over the last 20 years since codes were changed and the delegated design process started entering into the specifications. Before that, it was all done internally by the system manufacturers themselves.